All right, this big step. Today we're gonna take a big jump. We're gonna take, essentially, here's what this does for us. I've looked through the homework. It seemed to be doing real well on the earlier chapter 2 stuff. To put this in perspective, the first parts of chapter 2 give us some rules for differentiation. They allow us to differentiate power functions, some trig functions, products, quotients, but they're a little bit limited. Here's how they're limited. We're limited to functions that look exactly like the standard form. There's very little variation allowed. So for example, we can do this. If y equals, say, 3x to the negative 4, right, which would be the same thing as 3 over x to the 4th, we can find dy dx, right? What's our trick? Yeah, okay, we're just gonna, if we started here, we're gonna rewrite it, I guess, in this form. We write it as a power, and then we differentiate using the power rule, right? So what would I do here? Say it again. Okay, good. I bring the exponent down, so I get a negative 12 for my x. Yeah. And if I want to write it in terms of positive exponents, just negative 12 over x to the 5th. Okay, but where we're stuck. Where we're stuck is when we try to do something like this. What if y equals 3 times the quantity, say, x plus 1 to the negative 4? Now what do we do? I mean, we can't at this point. If I write that in terms of positive exponents, it looks like that. Whoops, like that. But I can't distribute this thing, right? I mean, it's... Oh, positive 4. Well, yeah, you're right. Yeah. Thank you. No, there was nothing, no trick there. That was just a mistake. We can't do this one. Right now, if this had been a positive 4, we could have done it. We could have just expanded this whole thing out and differentiated term by term. But we can only do that for terms in the numerator. If I have multiple terms in the denominator, I'm sunk. None of the standard forms fit. Good news, though. We have a way to expand our derivative rule for powers in such a way that we can do this using what's called the chain rule. Now, there's two ways to look at the chain rule. You can look at it. Here's the way I'm not going to look at it today. But we'll come back and do some more stuff with this later. I'll be gone tomorrow, but we'll come back later in the week and look at it this way. One way to write the chain rule is this way. But we're not going to look at it that way. Okay, this has to do with considering derivatives as rates of change. There's a really good, if I have time at the end, there's maybe one thing I'll do to kind of get you thinking about this a little bit. We'll come back later and look at some more practical applications of that approach to the chain rule. The approach we're going to take for today is really pragmatic. What we're going to do is we just want to know how do we take derivatives using the chain rule? What's our approach to taking a big ugly derivative and breaking it down into steps that we can deal with? And here's how that looks. Think of it like an onion. We'll call this the onion approach. Okay, and so if we're taking a derivative of a function of a function, so sometimes we call that in math a composition of functions. So what if y equals f of g of x? And we could go further. We could say f of g of h of x, or we could even go further than that with the chain rule. Once we know what the trick is for dealing with multiple layers of a function, we can extend that to as many layers as we want to. Here's what the chain rule tells us. It tells us that we're going to differentiate this thing from the outside in. So at the outermost level, if we forget about what the inside function is, I've just got f of something. right? And I'm gonna use the appropriate derivative rule that addresses whatever function f is. So the first layer, we might say the first link in the chain is gonna be the derivative of f. So it's gonna look like this. F prime of whatever's inside. And we don't even care at this point, we haven't even looked. We're just focusing on the outside layer of the onion. The next link in the chain is to peel the onion away and look inside. And whatever the inside function is, we'll multiply by the derivative of that function. And so we get two links. And those two links look like two factors that are being multiplied together. The first factor we can call link number 1, and the second factor link number 2, and that process could just continue. You know, we can just keep going with more and more links. As many layers as we have determines the number of links we have in the chain. So let's try one of these, see what it looks like. Let's try, how about, let's see. Sine of x squared. Okay, how many layers are there to that function? 2. Okay, what's the outermost layer? Sine. Okay, so at the outermost level, if we're looking outside in, we got that's a sine is the kind of function animal we're dealing with here, right? It's a sine. And we'll treat it like a sine. Now, when I peel away that layer, what have I got? X squared. Okay, I've got a power inside that, right? And so if I want to differentiate this then, y prime is going to equal, what's the derivative of sine tan? And I'm calling it hand. I know that sounds kind of dorky. I don't want you to look behind my hand. We're not worried about that. Just the sine of hand. Could be anything. Cosine hand, right? So we get cosine of hand, good, and then times the derivative of whatever's inside. Well, what's the derivative of what's inside? And now we can go back and figure out, well, what actually was in there? That was an x squared. Okay. Right? And when we're doing this, we would have written it in that order. But my point is, I want you to just ignore what's in there for now. Okay? And that's it. That's the answer. That's the answer to our derivative. And so if we wanted to write that in a little more convenient way, we'd probably put the 2x out front. But that's it. Okay? That's how we do it. So then, how do you suppose we could deal with our earlier dilemma? We had the function y equals, what did I say it was, 3? Okay, there we go. So how could I use this new trick to deal with that function? Okay, so first step would be, say it again. Okay, we'll write it as power, right? So we've got this 3 out front, and then we've got the quantity x plus 1 to the minus 4. Now let's be real specific about addressing this function here. What do we do? What about that 3? What do we do with the 3 out front? Is that a cause for concern? How do we deal with it? I know it's been a long weekend. Let me ask you this, do we have to treat this as a product? Because it looks like I've got two things multiplied. I've got 3 times this stuff. Yeah, exactly. What do I do with the constant? Pull it out front. Leave it there, right? So I think you were looking for something more profound than that. And that's all I'm getting at, is when we have a constant out in front, remember, we just leave it alone. And then at the very end, we can redistribute it if we need to, but we get to just forget about that. So the 3 is out there. Don't need to worry about that. Here's the part we're interested in, though. That guy. Now, how many layers are there to that function? I think I heard it. 2. Yeah, what's the outermost layer? Tan to the negative 4, right? And then inside that, I've got a derivative of, a pretty simple function, x plus 1, right? But it is a function, okay? And so we can deal with this using that chain rule, can't we? So, I'm running out of room. I'm going to go to the next page. What's going on? Uh-oh, that's not what I want to do. The problem is, I don't know what I'm doing either. Things are just happening here for, I don't know what's happening. My goodness. Oh, what was that? Okay, here we go. Gotta do that again. I didn't paste a copy instead of pasting that. There we go. Okay, so then I've got my 3 I can just leave out front. I've got the derivative of hand to the -4 is what?
4 and negative.
There you go. Okay. So times -4 hand to the -5. And then what's the derivative of hand? What's the derivative of x plus 1? Yeah. And so if we look inside, hand was just an x plus 1, right? And well, we got to clean it up. That's the answer.
Why don't you take the derivative of 3? Like, why doesn't it go to 0?
Well, okay, you could. You could. Now, I'll give you an example here. Hold that thought for just a second. I'll show you. I'll remind you why we don't do that. Okay. Now, we're done with the calculus, but as you're going to come to expect doing these problems, honestly, algebra makes up at least half, if not 3/4 of the class. It's just algebra. Just getting. You're going to be so good at algebra by the time the year's over. Seriously, your algebra skills today, you just. I mean, you're good now, but you'll be great then. What do we do with this to make it look better? Yeah, 3 times -4 times 1, so I just get y prime equals -12, and then what about all this stuff? Okay. Or, I mean, we could leave it as a negative exponent, but typically, it's just better, it's easier to understand if you write it in terms of positive exponents. So there's our answer. Okay, question was asked. Mr. Rickman had a question for us. He said, what about that 3? Well, let's pick a slightly easier problem. What if we have, say, 3x squared? Now, we could treat this as a product. We could say that u is 3, it's something like grammar. U is equal to 3, I should say, and v equals x squared, right? Okay. If I use the product rule, then I would say 3 times the derivative of x squared, right, plus x squared times the derivative of 3. But what's the derivative of 3? Okay, and so, is it necessary? No. The product rule ends up being a waste of time because the derivative, that term, is always going to disappear. And so that's why instead we just have the constant multiple rule. Whenever we have a constant out in front of a derivative, in fact, we could write it like this. If we really wanted to, we could make a little rule out of this that says the derivative with respect to x of c times f of x just equals c times f prime of x. Meaning, the constant just gets pulled out front. We just differentiate the function part. Okay? All right. You guys need a challenge. This isn't hard enough yet. I gotta find something better for it. Okay, how about okay, I know one thing we can do. This will be kind of cool. Let's prove let's just, now that we have this chain rule, let's prove I just kinda gave you some trig, derivatives the other day, and you just believe me. I'm a pretty believable guy, I understand, but maybe if you're just a little dubious about this, let's prove it for ourselves. Derivative of secant x. Now we could write this in terms of sines and cosines, and now we can get an answer out of this. Okay, we could write this as the derivative with respect to x of what's secant? 1 over cosine x. Okay, so now how can we write this in a way where the chain rule might be helpful to us? Okay, we could write this as the quantity cosine x to the negative 1. So the derivative with respect to x of cosine x to the minus 1. Okay, now if we're going to differentiate this using the chain rule, using our onion approach, what's the outermost layer of this function? Yeah, hand to the negative 1, right? Okay, and what's the derivative of hand to the negative 1? Yeah, right. Bring the power down. Negative 1 hand to the negative 2. Everybody agree? That's our first layer. Okay, so negative 1 times hand to the negative 2. And then if we peel away the outside layer of the onion, what's the derivative of the next layer? Negative sine. Okay, times. Okay, and then inside, you had a cosine. All right, so what's that look like then? If we clean this up, what could I do here? Okay, sine of x, and you saw that negative times negative. If I have three factors here, right? I have the negative 1, the cosine x to the negative 2, and the negative sine x. And an even number of those are negative, so those negatives will cancel, and I get a positive result. And the sine x stays on top. Now what? Well, the negatives canceled. These guys canceled. Okay, good. So on the bottom I've got a, good, which I can abbreviate cosine squared x. Okay, now I can split them. Good. So I could write that as, good, 1 over cosine times sine over cosine. Everybody agree? Okay. And what is 1 over cosine? What is sine over cosine? That fits our pattern, doesn't it? Right? So we got it. Okay? We proved it. That wasn't blind. All right, well, let's try one with more layers. Doesn't seem like that's challenging enough. Let's try one that's got more layers to it. How about... If you can do this one, this is the granddaddy of all chain rule problems. If you can do this one, you can do any of them. And you can do this one. So that's good news. What's that?
I do this enough to hurt on my head.
Yeah. Well, before we do the granddaddy, we'll do one warm-up. How about?
Ready to go, buddy.
Okay, what about that one? Everybody stare at that for a second.
Why you hate us?
Okay, there's a couple ways to look at this, and they're probably equally good. We're going to arrive at the same place, but how many layers are there to that function? Okay, I'm seeing 2, and I'm hearing 3 and 2. Both are reasonable. If you said 3, how would you identify the layers? What's the outermost layer if you said 3? Okay, cube root. Then what's the next layer? Squared. Okay. And then finally, that's okay. Hand that back to 2. Are you healthy again, Teo?
Yes.
All right. So first layer cube root, second layer squared, third layer the polynomial x squared minus 1. That works. That's one way to do it. If you said 2 layers, maybe you found a way to shorten this just a bit. What's the 2 layers? Okay, good. We could say we know. Maybe we could make it a little shorter. We know that the nth root of a to the m, I could write as a to the m over n power, right? So maybe we could make it just 2 layers. Maybe we could write it as a 2/3 power. We could rewrite it like this. And this isn't a bad idea to actually physically rewrite it, especially when you're dealing with radicals. We're going to do this a lot in calculus. Radicals are a convenient way. In some contexts, it's convenient to use radicals. But in calculus, when we use the power rule, a lot of times we'd rather write those as fractional powers. So we've got x squared minus 1 to the 3/2. Whoops, I did that backwards, didn't I? Not 3/2, 2/3. Okay, and so then this is not a big deal to differentiate. First link would be what then? Yeah, good. 2/3 hand to the. Okay, did everybody see that? 2/3 minus 1 would be negative 1/3. We are exponent. Okay, so there's our first link. And then the second link would be, if I look inside, it's 2x, isn't it? Okay. And we got it. Well, we could clean that up a little bit. Now, just for practice, I guess, stare at that for a second and see if you can tell me what the finished form would look like if I simplify that. What's going to go on the top? Okay. 4/3 x, but that we don't really want to have a fraction in the top if we can avoid it. 4x, yeah, the 3 is going to go down to the denominator, right? And we get 2 times 2x, so we get 4x on the top, on the bottom, 3 times x squared minus 1 to the 1/3. If we really want to, we could even write that as 4x over 3 times the cube root of x squared minus 1, right? Okay. All right. Maybe one more. How much time we got? Oh, yeah, we're good. One more before we get to the granddaddy. Let's try, how about, oh, I know it'd be good. So what about that one? Okay, stare it down a little bit. And the staring part is good in calculus. Before you jump into this, you really got to identify what is this, what kind of animal we're dealing with. At the outermost level, what rules apply? Okay, now this one's a little different than the last couple we've looked at, right? The last couple we've looked at have been definitely chain rule, multi-layer problems, but there's another wrinkle thrown in. What's that? Ah, good. Product. We have a product, and then within the product, we got a multi-layer. Yeah, how about that? Right? Ooh. Okay, so we got the yellow bubble. There's one of the factors in the product, right? And then here's the green bubble is the other factor in the product. So at the outermost level, this is just a product rule problem, right? So U is x squared, V is the sine function, right? Right? Ooh, okay. So what's the product rule tell us then? Now let's do this in broad strokes here first. Let's not try to get too specific. At the outermost level, what is the product rule informing us here? What do we have to do? Okay, good. Okay, so first, so yellow bubble times derivative of green bubble plus green bubble times derivative of yellow bubble, right? Okay. All right. So if you didn't know the context of this, and you walked into class, that would probably sound a little strange. Okay, so yeah. Okay, so now if we're going to take the derivative of the green bubble, right? We got yellow times derivative of green. What's the derivative of the green going to look like? That's a chain rule deal, isn't it? That's an onion approach. Focusing on the green bubble only, what's the outer layer? Sine of hand, right? Good. Okay, so what's the derivative of sine of hand? Cosine of hand. Okay. Okay, and then if I look at hand, what is hand? Okay. Okay. So I've got an x plus 1 to the 1/2, and I probably should even write it that way. In fact, I'm going to do that just so there's no confusion here. I could rewrite this whole thing as x squared times sine of the quantity x plus 1 to the 1/2, right? So then if I take the derivative of the next layer inside the sine, notice that's hand to the 1/2. What's the derivative of hand to the 1/2? Now everyone focus on this, please. Derivative of hand to the 1/2. Say it again. Somebody said it correctly. Good. Okay, 1/2 hand to the negative 1/2. So let's change colors for the next link. Right? And let's start filling in some hands here. So the first hand was an x plus 1 to the 1/2. Right? We took the cosine of all that stuff. Derivative of sine of all that stuff was cosine of all that stuff. When I peel it away, the derivative of, other hand, left hand to the 1/2 is 1/2 times left hand to the negative 1/2. Well, what's left hand? And then finally, if I peeled away the sine, I peeled away the 1/2, I'm just left with an x plus 1. What's the derivative of that? 1. Okay. So the last link we could not even write. That's just a 1. Wow. Okay, and that's only half of it. That's the hard half though, right? Okay. Now we have to do green times derivative of yellow, right?
Yeah.
So we've got sine of, I gotta go to the next line. Oops. So there's green. What's the derivative of yellow? 2x, okay. Okay. So we're done with the calculus. That's it. Done with the calculus. Now we have to just clean this stuff up a little bit. And so the second term is pretty easy. Second term is just going to be 2x times the sine of square root of x plus 1. But that first term is a little bit ugly. What are we going to do with that? It's going to be a fraction, it looks like. What goes on the top of the fraction? Yeah, it looks like I have an x squared up there, right? we'll just kinda tick these things off as we go, so that one's out of there, now what? Cosine, okay. Of, yeah, we just call it the square root of x plus 1, how about? Okay, so that's gone then, right? Divided by 2. Square root of x plus 1. That negative puts it on the bottom, right? And the 1/2 makes it a square root. Everybody good with that? Okay. And then the 1 here. So there's our first term. Plus, and then this is pretty easy. 2x sine square root x plus 1. Wow. Okay, make sense? I mean, as difficult, that's a lot of stuff, but as difficult as that process would look if you just didn't know what you were doing, if you think back on it, there's a method to this, right? And that's, I'll tell you what, differential calculus, I know right now differential calculus definitely, correct me if I'm wrong, seems probably kind of hard. But you'll look back on this in a few months and you'll say, yeah, differential calculus is really just a matter of following the rules. That's all you do. There's a set of rules and you have to determine which rule applies, and then you just follow those rules. Integral calculus gets a little trickier because you have to kind of play like Jeopardy. You got to think backwards. But differential calculus is just a matter of following the derivative rules. Okay? So you ready for the granddaddy? That was kind of a grand. That was. Yeah, I don't know. That was the great uncle. This is the granddaddy. So, actually, I think that one might even be harder because it had a product rule in it also. Okay, that doesn't look that bad, but there are a lot of layers there. There's a lot of stuff going on. How many layers are there to that? Seeing 2?
2 in product rules.
Okay, more than 2. How many? I'm hearing 4. Is everybody buying that?
3.
Okay, see if we can identify the 4 layers. Somebody call out, what's the first layer? The outside layer of this. This is a tricky one. Square. Yes, it is. Okay, here's the first thing I want to tell you about that's important. At least initially, everybody should do this. After a while, maybe you don't need to, but when you see a shorthand trig power like that, and that's when we write tangent squared of hand, what we really mean is tangent of hand quantity squared, right? It's just easier to write this way. That's what that means. Don't lose sight of that. So we want to rewrite this thing as, I guess, we'll do it this way. I've got a power on the outside. Inside, I've got a tangent of something, right? And what's the tangent of, well, what's the something inside the tangent? Square root of x squared minus 1, which we probably need to write as what? To the 1/2. Okay, well, I got too many people. You got to really focus on this one. This is the granddaddy. You got to follow all these layers. Everybody with me here? And then this is the last big example. So the square root of x squared minus 1, we got to write as fractional power. So let's do that. I can't do that because I can't distribute the 1/2. Remember, you can't distribute a power, unfortunately. right? For example, if I have a plus b squared, remember that's not equal to a squared plus b squared. I have to, right, you can't distribute powers. You can't distribute powers over sums and differences. Okay? Be nice if you could, but I'm not gonna roll. The math gods didn't want it that way, I guess. I don't know. Okay, so there we go. Now we've rewritten it in a way where we can see all the steps more discreetly, right? So if we're going to differentiate this, we got 4 layers, so we should expect to have 4 links in our chain, right? So y prime equals outermost layer we said was double hand to the 2 is what?
2 double hand. 2 to the negative on 2.
Okay, so we're going to get first layer. We're going to bring the 2 down front. 2 times double hand to the 1, right? Okay, and then what's inside? Tangent of the quantity x squared minus 1 squared, right? Okay, then we had inside the squared, we had a tangent of some stuff. Derivative of tangent is heard it. Secant squared.
Isn't that 2 supposed to be 1?
1/2. You're right. You're right. There we go.
I heard that one after.
Okay, so the derivative of tangent something is secant squared something, right? So we got another link. So there's our x squared minus 1 to the 1/2, right? Now what's inside that then? I've gotten rid of all that stuff, right? Now what? Yeah. Then I've got a hand to the 1/2. The derivative of hand to the 1/2 is times 1/2 hand to the and hand in this case is just x squared minus 1. And then finally, my 4th link in the chain. What's the derivative of the inside, the very inside of the onion? 2x. Calculus is done. Yeah. The calculus is done. Now we just got to clean it up a little algebra. So this looks like we're going to have some stuff on the top and some stuff on the bottom. So let's make a big fraction out of this, right? Okay, so what's going to go on this? Well, any cancellation? Yeah, the 1/2 is going to cancel with a 2, isn't it? Take your pick, either that 2 or this 2, doesn't matter. So I can cancel that guy with that 2. Good. And then we're stuck with, what's going to be stuck on the bottom? There's only one thing on the bottom, so let's just get rid of that. Okay, and if it's to the negative 1/2, square root on the bottom, right? Okay. So we get square root of x squared minus 1. Good, so we can get rid of that stuff. He's taken care of. Now I've got a bunch of stuff on the top. If we want to write this in a nice, pretty way, what should go first? Yeah, we got the 2 and then the x, right? We want to get the constants, variables, and then we'll get the complicated stuff, right? So we get, whoops. 30 seconds. Oh, we got to hustle. So we got 2x, those guys are gone. And then it looks like we've got a tangent of the square root of x squared minus 1, right? Times a secant squared of the same thing, right? This gray is kind of bad. Sorry, I just didn't want to take time to change it. And that's it.
Are we just gonna ladder up?
Yeah, you guys get to left.